in the last class, electromagnetic induction. Okay, and I hope and I believe everyone know this. What is a EMI? Electromagnetic induction is a phenomenon. EMI is already written down thing. So electromagnetic induction. Okay, what it is? This is not not big thing or a rocket science. Simple thing. As we know, whenever a current is passing through any particular coil, so it generates a magnetic field. So we need to see the reverse effect also. Simple as that. Whenever we move a magnet, so is there a current is going to be generated, or is there a production or a generation of current is going to be? Yes, it is. Simple. Okay, so this particular process, this particular phenomenon is known as electromagnetic induction. The main thing here is relative motion. Okay, relative motion in between coil, relative motion in between the coil and magnet is necessary. So either you can say the main thing, or you can say the necessity of this particular thing or this particular phenomenon is this relative motion. Is this clear, everyone? Fair enough? Clear na? The main thing to generation of this particular thing or this particular phenomenon, EMI, is this relative motion. We already done this thing. Okay, now I give you the statement of this about Lenz law also, and if anyone not attend that particular lecture, so it's not a big deal. I mean, it's not going to be big deal. Lenz law, what it is states that, let's do this. So the induction, or you can say the induced current in a circuit due to electromagnetic induction always oppose the change in a magnetic flux. As simple as that. You can correlate with the Newton's third law of motion. Newton's third law of motion states that whenever you apply a force on any particular object, so that particular object apply the same force in a reverse effect. That is Newton's third law, right? For example, if there is a ball here and you are going to kick this particular ball, okay, in this physical health you cannot kick this, but it's assume that you are going to kick this particular ball. So how much the force you apply with this your leg, malnourished person right now, trying to apply the force on a ball here. what I'm saying. So the same force is going to be applied on this particular person's leg or on this particular boy or a girl leg in a reverse effect by the ball. Okay. So this effect is going to be on two way thing. I mean the reverse force is not going to be applied on the same object. The main thing is this. In a same sense, if there is a production of current, as we know, as we see, whenever we move this particular magnet in this way, so there is a current is going to be generated. Okay, so this current is try to oppose this. If it is moving in this direction, means this magnet is moving in this direction and the current is moving in this direction. It is try to oppose this. This is the normal human tendency, not normal human any physical system tendency, not human tendency. For example, if I'm saying you guys so many times, better turn on your camera, you are not willing to do that. I don't know for which particular reason. Is this clear? So even in this class, you're going to shut in between, and that is very quite understandable thing. No one wants to turn, you can say this camera thing is going to be, and I don't want to, but if I see the black windows so much time, so that is going to be the effect. Okay, because then I realize, or then I think you are there or not. Is this clear? So coming back to the topic, what is Lenz law? Lenz law states that is very simple. It is going to be give you the energy conservation law. Means whenever there is a current is going to be produced by the motion of by the relative motion of a coil or a magnet in a coil, so the current is going to be flow in the opposite direction of the flow of motion, or of the flow of magnet, or of the flow of magnetic field. That is in general a Lenz law. And why it is happening? To conserve the energy. As simple as that. Because we learn in 9th class or in 8th class, energy conservation states that energy can neither be created nor be destroyed. So there is some opposite energy is going to be apply in that particular physical system to maintain the entire energy zero. Is this clear, everyone? Because we apply energy to move this magnet in this side. Suppose this is the magnet, so the current is going to be in opposite sense. So this motion and the motion of current is going to cancel each other. The net energy is going to be zero again. Simple as clear. That is written over here. Let's read it out. It is a scientific law that states, that specifies the direction of induced current. Okay, I mean that induced current direction it gives, but it states nothing about its magnitude. Clear enough? Means it just tell about, your Lenz law tells about the direction only, nothing about magnitude. Magnitude we are going to find out with the help of formula or with the help of your relation. EMF relation, E equals to minus d phi by dt. E can be dated as a potential difference. So I, which is V by R, E by R minus d phi by dt, or you can say 1 by R d phi by dt. Simple. The magnetic field associated with the closed circuit amplifies the current, amplifies the induced current flow in such a way that it creates a magnetic field in the opposite direction of the original magnetic field. Now what it states, that very important thing, and you need to focus here. What it states, that suppose there is a coil. Okay, in a reverse, you can understand more. Suppose there is a coil. Obviously, whenever there is a coil, so or in any particular coil, so I apply here. This is my, okay. Suppose there is a closed circuit. In this particular closed circuit, the current is going to be generated. Or in any particular coil, when the current is going to be generated, so beta, it is quite easy to understand. There is a magnetic field is going to be generated also, isn't it? Because that the same thing is going to be happen. Just a minute, beta. So what happening here in general, the magnetic field is going to be in this way, north to south. Clear? The arrow is going to show the represent of a direction of a magnetic field. So the production of this particular current is going to be in this way, southwise. Southwise means in this manner. So this particular pole becomes south, or this particular pole become north. Simple. If it is becomes south, so my current is going to be in this way. This is my I induce. So what is going to be happening here? Understand very carefully. Initially what happens? Wait. If it is going to be south, so it is going to be attract. See, if it is south here, I reverse my polarity. Yeah. In this particular sense, south becomes this. Rewrite again the same thing. Now it is correct. So if I repeat, yeah. In this way, the south pole become here because the current is flow in this way. So this pole becomes south because current is flowing in this way, or you can say in this way. So obviously this is the symbol of a south. I explained this south north in the previous class very clearly, right? If you have a doubt, so please go through this. After this class you can check it out. So obviously if this particular side becomes a south, understand in this way, because we know this terminology also. Whenever there is a current flowing in any particular wire or a loop, so this become a kind of a solenoid, or this behave as a temporary magnet. Is this clear? Temporary magnet. So due to sorry, due to this I induced, okay, due to this induced current, due to this motion of this particular thing, due to the magnetic field flowing through this becomes a temporary magnet until unless you are moving this. Clear? So this becomes south. Initially it opposes this. Obviously it is going to oppose, it is going to repel this because it is a north, it is a north. And the same thing when this magnet is trying to go away from this. Okay, when it is trying to go away from this, so now it is north, now it is south, it is also still opposing this. Clear? Opposing in what sense? Because it is a south, it is a south. So they are, both the poles are same, and when both the poles are same, so they're going to repel each other. Is this clear, everyone? So this is happening here, and that is why we say that the magnetic field, understand, I mean, now read this particular line once again. The magnetic field associated with the closed circuit amplify the current flow in such a way that creates a magnetic field in the opposite direction of the original magnetic field. Clear? Because as you can see, here it is north, here it is south. So this particular coil having induced current generates or creates a north pole in this side or south pole in this side, opposite to this. Is this clear, beta? If I can change the polars, or you can say polarity, what happening then? If I make south here or north here, so it is going to be attract. I'm repeating, beta. I'm not done yet. Yajira. What I'm saying, understand in this way. See, this is a little tricky part, and then you can everything are going to understand that because easy after this. See what happens, there is a coil. Okay, I apply a coil in this particular pen, and then I give this particular coil a current. So this coil become a magnet itself. First thing, we done this particular in the previous chapter, right, Yajira? Good. Now what I'm doing in the previous class, what we done, whenever there is a magnetic field is passing through in a coil, or a coil is passing through a magnetic field, so there is a production of current in the coil. Clear? So due to this production of current, due to this induced current, this coil itself become a magnet. And this magnetic field is opposite to the original magnetic field. Now my original magnetic field is in this direction. Means this is north and this is south. I mean in this means north to south. So the temporary magnet. Why should I say temporary? Because the magnetic field in this coil is going to be till now, till that particular moment, the moment I have a movement, right? Relative motion. The moment I stop my relative motion, current is going to be stopped, and this coil become again a coil, not a magnet. But the generated magnetic field due to induced current is in the opposite direction. Or this is going to oppose. Initially it is north, so they repel each other. They try to repel, but it is not going to, because my relative motion is, you can say, more enough. And when at the end my south is trying to away, then it is also repel. Clear? Clear na? Good. So that is why I make this thing. So this below sign is wrong. It is not going to, because if it is happening, so that is going to attract, but this is right. What happens to me right now? Is this clear? In south north is very easy. The guys who don't know, if in any particular coil, I'm talking about coil, there is a coil. Okay, if in this particular circular coil the current is flowing in this way, so what does this mean? South. So this particular coil gives me the south pole of a magnet. If it is going to be reverse, that is how you can understand, and that is how you can correlate. If it is going to be in this way, so how it becomes north? Simple. Clear? Clear? Clear na? Good. So that is the scene here. I mean that is the concept is going to be. And as I already tell you this thing, this is the opposing the cause which produce it is starting, and it's simulated with the Newton's third law. Means it is going to oppose the particular cause. Cause means here. Why should I give you this example of football? Cause is kicking the football, and that particular football applying a force on the your leg. Clear? I mean, you feel that particular force on your leg, na? And the same in a bat ball. Whenever we hit a ball with the bat, so there is a sensation is going to be on the bat itself. The recoil system of a gun, and you can say bullet. Whenever we fire a bullet, so there is a recoil on the bullet. Clear? Is this clear? Na? That is Newton's third law, going to oppose its cause. That is the meaning of saying that. Is this clear? Because it is important. After that, we have a formulation and everything. Is this clear, beta, everyone? Good. Okay. So now this is uses of Lenz's law, or you can say Lenz law. The braking system in train works on the principle of Lenz law, and that is very important. Maybe you hear that particular name of bullet train, which is run with the very high speed with the electricity. So there we use magnetic brains. Okay, magnetic brains. Not brains, but I'm saying magnetic brakes. Magnetic brains is the something name. Okay, so that is magnetic brakes. Magnetic brakes apply on this particular principle. Okay, AC generator works on the principle of Lenz law. Eddy currents are balanced using Lenz law. There is a phenomenon known as eddy current. I'm going to discuss. If it is not discussed yet. Okay, metal detectors, card readers, and many other electronic devices are used the concept of Lenz law for their application. Like I give you this example or this real life use in the previous class. For example, whenever there is a counting system, reading system, or everyone here know about the debit card, credit card nowadays. I believe that. So how they fetch your data? Fetch your data means the moment you, insert your card in the ATM and just put a number. I mean, putting a number is a secondary thing. You select few things and then give your one OTP or a kind of a code, or you can say a password. Not a code is a good thing. A password kind of word. Okay, password is there is a 6-digit, 4-digit, and then this particular data is there is a magnetic strip on that particular card cards, debit card, credit card. From there they already know who you are, which particular bank is this related to. Okay, obviously right now you don't have your personal bank maybe, or if you have, that is very good. But you know about debit card and credit card. The black color line is there, sir. But I don't know about the black color line. But yes, there is a maybe that black. No, not black color line. There is a gold something look like this, or there is a strip in this way. One of the two. I don't have my credit card, debit card right now. Some chip will be there. Yeah, exactly. The local name is chip. Okay, in the front end, when you enter, sometimes when you enter from the back side, so that is not going to accept. There is a particular process to entering or inserting that particular debit card, right? So there is a gold color or a golden color something, both will be there, sir. Chip and magnetic character. Magnetic character is behind. There is a something in this way, or a strip, and then there is a this way. Lines are going to be. So this particular thing in the front end. Okay. So this is one of the. Now Lenz law formula. We already understood this. We already know this thing in the previous class. So according to this law, EMF on the coil is calculated as N number of coils in a number of turns in a particular coil. Phi is a magnetic field. Okay. For those who are absent in this, I'm going to write phi only, not phi B again and again. Phi is a magnetic flux, B dot A. In great detail, you can go through the previous lecture, B A cos theta. Okay. And then whenever there is a magnetic flux is passing through any particular coil, suppose there is this your coil, and again there is a magnet. Okay, so if there is a I need to take a 5 minutes break now, I think. North to south. So there is a current is going to be generated in this. Suppose there is a ammeter or a galvanometer. So you can see a current in this, a deflection in this. Okay, there is a current is going to be generated in this way. So obviously, if it is a magnet, so in this particular area, in this particular region, there is a area into magnetic field, which is a magnetic flux, and this suppose N is number of turns. So EMF. Now, how much electromotive force is going to be apply on this particular coil? This is your this particular formula. EMF E equals to minus N d phi by dt. As I already mentioned in the previous lecture, like this negative sign already states that the induced EMF is going to be in the opposite sense. And that is written over here. Okay, read it out, beta. I'm just coming in a 5 minutes. I need to go. Hello, hello, hello. Yeah. Okay. So is this understood? Is this clear? Hello, hello, hello. So according to this particular law or Lenz law, EMF is going to be generated E equals to minus d phi by dt. This negative sign indicates that the direction of induced EMF is such that it is opposed the change of magnetic flux. Change of magnetic flux means obviously if you, I mean, in a continuous motion, or you can say continue move this thing. Okay, move is the correct one, or you can say movement. Continuously move this particular magnet, so magnetic flux is going to be decreases, initially increases and it decreases. So magnetic flux is going to be change. E is electromagnetic force and is number of loops in the coil. This particular number defines the change in magnetic flux. dt is change in time. Simple as that. Okay, Lenz law experiment. Now there are few experiment like we going to understand movement of wire or electron flow. So I mean the same thing is happening here. Instead of I move my you can say coil, instead of changing magnet, what I'm saying, instead of moving magnet, like the second experiment, if you remember, of which particular Hertz experiment or what particular experiment, I mean I don't remember the name right now, but can you brief me the name of these experiments? In the previous class we done na? Right now I don't know. Okay, leave it. Anyone tell me which particular experiments we EMI, Hertz experiment known, or which particular experiment these are? The name I want to know. I am confused in the name of these particular experiments. Electromagnetic induction, if I'm not wrong, gives by the Hertz. Which particular experiment? You note it down na somewhere. Okay, so the experiment, like there are 2-3 experiments. Either we can change the magnetic field by changing the by moving the magnet. We can change the magnetic field by moving the coil, or we can change the magnet by changing the temporary magnetic field by moving the temporary magnet, another coil. So in the same way we can move the wire. Okay, there is a magnetic field, as you can see here. The magnetic field is going to be in this direction, and whenever the magnetic field is going to be in this direction and I rotate, instead of rotate, I move this particular wire in this way. Okay, I move this particular wire in this way. So there is a EMI production is EMI phenomenon is going to be there, and EMI is going to generate a current in the opposite direction. As simple as that, and that is the basis of this AC generator. Clear? This particular picture is describe this. Is this clear? We're going to understood this thing in a more great detail. I just change my you can say relative motion and scenarios here. Nothing more is going to be changed. Instead of a coil, I pick a wire. The same thing is going to be a wire in a wire. Electron flow shows me the current, or you can say induced current. Is this clear? Movement of wire can be up and down, as you can see the movement of wire in this way. So the electron of flow is going to be in this way. Clear, everyone? Clear na? Good. So the first experiment, or you can say Lenz law experiments, these particular important for board aspect, and whatever written over there I'm going to explain. So first experiment, by Lenz proved that the current flowing in the coil produce a magnetic field in the circuit, and the strength of the magnetic field increases with an increase in the strength of the induced current. Also, this magnetic field produced oppose the original magnetic field. That is, the direction of induced current is opposite to the original magnetic field. Very simple, very basic. We already done this thing. There is a coil. Okay, in this coil I apply a galvanometer to check how much current is this. Okay, and I use this magnetic field, or there is a magnet here, north, south. So simple thing, if I move this particular magnet in this way, so my current in this particular coil is going to be moving this way, and due to this there is a north pole here and there is a south pole here is going to be generated. Simple written thing. This is your first experiment. Is this clear? And that is experimental thing. Okay, experimental thing. This is not something you can say where from this particular ideas come. Whenever any particular scientist do an experiment, so he or she all combination permutation try, right? If you are doing any new experiment and you want to find the result, so you recheck every particular possibility whatever comes in your at that particular mind, and on that particular so many possibility, whatever the 3 or 4 or 5 important aspect you noted down, you took it as a final experiments. Okay, you can ask, sir, what happened if I change the wire? Obviously, if instead of diamagnetic I pick a paramagnetic or a ferromagnetic, obviously the magnetic field is going to be changed, because it is a ferromagnetic material, right? In ferromagnetic material, the magnetic intensity or magnetic field is, or this property is going to be more as compared to the para or di. So every particular aspect they check, but due to this particular field, whatever the aspect is remaining on this, that's we're going to discuss. Is this clear? If any one of you guys thinking, I think in this way when I was learning first time, sir, what happen if I put this particular thing in a water? Obviously the thing is going to be changed. What if I change the surrounding? Obviously, what if I use a plastic? So for plastic it is not going to happen. Maybe some of you thinking in this way, I think in this way. What if I apply a plastic here? Where? Wait, I'm showing you where. Here. I mean, I laminate this thing, but with non-conductor. If I laminate this thing with non-conductor, so there is a no current is going to be, or current is going to be flow. So the magnetic field due to this induced current is going to be very less. Okay, because I don't remove the wire, I just apply an extra layer of non-conductor, which is a rubber maybe, or which is a plastic maybe. It's my choice. PVC, polyvinyl chloride. There is a product with which we can make not max, I mean not more than 95% things nowadays look like a plastic. That is PVC. Your chair, your wires, your any particular thing looking like a plastic thing, that is PVC. Okay. You can say I'm telling you the molecular name or a chemical name with which plastic is made of. Polythene. Poly means so many. Ethene means a chemical name. That is the thing. And from there is a PVC. Okay. So let's come to the basic. Second experiment. So second experiment by Lenz states that the iron rod wound by the current carrying, okay, let's read it first and then I'll explain. Lenz states that iron rod wound by current carrying wire, its left end behave as a north pole if moves towards the coil and induced current is produced in the coil. I already tell you this thing. I don't need to teach this again. This particular thing they all discuss, where this thing means if I took a road, okay, more importantly on this particular page I can tell you, if I took a road, okay, in this way, suppose there is an iron rod. On this particular iron rod, there's an iron rod of mine, and I rotate wire on this particular iron rod. Why iron rod? You can ask me. Why not any particular? Because there is a conductor. So, beta, what happens? Now this becomes a solenoid, isn't it? It is a proper solenoid. But it becomes solenoid only and only when I pick this. What is this? Means a when I pick a magnet and moving this particular magnet, not this color again, moving this particular magnet towards this. Clear? So again, EMI production, EMI phenomenon is going to be electromagnetic phenomenon, electromagnetic induction. Due to this electromagnetic induction, if it is going to oppose, so this particular end necessarily needs to be north, this particular end necessarily needs to be south, and the current direction in this way. Again the same thing, I induce. Is this clear, everyone? Then it is going to oppose, na? As I already explained. Clear, na, everyone? Kaila, Sai, Shrutika, Yajira, Darshan, Dharmeshwar, Sushita. Everyone. Clear? Good. Yeah. Third experiment. See, I am going very slow. It's already 8 o'clock going to be in 17 minutes. So the third experiment by Lenz, because that is need to be explained. The next thing I am not going to explain. There is a formula. Relation belongs to the 10th class or the previous classes. I'm not going to explain. Don't worry about it. Third experiment by the Lenz state that the coil is pulled towards the magnetic flux. The magnetic flux linked with the coil decreases the area of the coil inside the magnetic field. Inside the magnetic field decreases. Now the induced current in the same direction. Okay, now the induced current in the same direction opposes the motion of the coil according to Lenz law. Now it is important. What it is says, understand in this way. Suppose this is my coil now. Clear? This is my coil and this is my magnet. So right now we are discussing till this point. What if it is going to be here? Obviously this is going to be here at particular moment, at particular position B. This is your initial position, moving in this way, again north south. Now it is B, again north south. The north south of this magnet, because it is a temporary permanent, it is not going to change, but this is going to be changed because it is a temporary, so the poles is going to be changed, isn't it? If you think, listen me again. What I'm saying, listen me again with very carefully or with very focused thing. I'm saying this is a permanent magnet. So permanent magnet. Permanent magnet have a fixed north-south poles. Clear? But this is a temporary magnet. So beta, if the magnet is a temporary, so the poles also be temporary, isn't it? So the moment you change the position, magnet, or the motion, or the current direction, or the current strength, the poles is going, I mean not the poles is going to be just changed because of the position of initial permanent magnet. Simple. Every other aspect like strength of a magnetic field, direction of a current, and so is going to be dependent on the motion or the position, both altogether. Now you can see, if this particular coil needs to oppose this, so this particular end right now at that particular moment, or at the moment, or at the particular position of permanent magnet B, it becomes north. Initially I say that is south. Right now I am saying it is north. Is this clear or not? Because the main thing of this particular coil is to oppose, not any particular, you can say other thing. Clear na? Understood? Because now at this particular moment B, my north pole is here. So obviously if this coil is try to oppose this particular flux, so this end right now needs to be become north. Clear? Is this clear, beta? Now what is written over here? Let's discuss on this. The third experiment by Lenz law states that if the coil pulled towards the magnetic flux, clear, means until, I mean till now what we are doing, moving our magnet towards this coil. In this they change the game. Change the game means they change the, I mean they did the variation in motion. This is your galvanometer, this is your coil, this is your magnet, north, south. Now this magnet is not moving, this is moving, coil is moving, motion in a coil, or you can say moving coil, moving coil. Now coil is moving, that is written over here. Okay, Lenz will say that if the coil is pulled towards the magnetic flux, so there is a magnetic flux and that is going to be pulled towards this. The flux linked with the coil decreases the area of the coil. Means the moment this coil is here now, the moment it is going to be the same thing scenario. Now this coil is here. This is your galvanometer. Now when this particular coil at this moment B, okay, decrease, you can say the magnetic flux linked with the coil, the magnetic flux linked with this particular coil, there is a magnetic flux is going to be, obviously it is going to be because it is moving and it is moving, so there is I induction, or you can say I induced, and there is a magnetic flux. Simple as that. Understood? So the coil decreases the area of the coil, or you can say magnetic flux linked with the coil decreases the area of the coil inside the magnetic field decreases. Now the induced current in the same direction opposes the motion of coil. Understand it? Again, when this particular position, so this coil shrink it down, and this coil is shrink it down. What it does basically, the current is start rotating, or you can say current is start flowing in a opposite direction to oppose the motion of this particular coil, not magnet. Now my magnet is straight here. Now I move my coil towards this. The moment my coil is at simultaneous position to the magnet, so the current is changing its direction to change the direction of a magnetic field to oppose the flow of this coil. Okay, or the coil radius, the coil area is changed. It shrink it down because your magnetic flux is depend on two things. Suppose for theta equals to 0 degree, magnetic flux is this. Okay, for theta equals to this, magnetic flux is this. So now my magnetic flux depend on area also. It is not only and only depend on magnetic field. Is this clear? Is this clear now? Is this clear, everyone? Good. So that is written over here. Okay, now moving ahead. Now this is just a formula thing, nothing more than that. Quickly do this. Induce current and induce charge, but it is important. We are going to do this in a little bit lesser time, but it is important, and that is nothing new, and that is nothing as you cannot understood. If a coil N turns, the rate of change of magnetic flux is del phi by del t, clear enough. Then the induced EMF in the circuit is this, or maximum number of times you find this particular symbol, which is the induced EMF minus N d phi upon dt. Okay, stick this symbol or a formula in your head for this particular chapter at least. Very important. Formula number 1. Good. So this is EMF. I already introduced this. EMF can be taken as a voltage. What voltage do? Voltage derive, or you can say voltage apply a force, or voltage did the work done. Okay. In general, how we define voltage? Anyone? What is the voltage formula related to the work or charge? Tell me. I want to write it, but I want to check your knowledge. W by Q. Exactly. So as we know, voltage is work done upon Q. This work done is what? What is work done? To move a charge in a wire. Clear na? So the same thing is happening here. Electromotive force. If a force is applying on any particular charge particle and that charge particle moves, so force into movement, work done. Now if I want to find per unit charge, I voltage. Is this clear? This concept is clear na? We can take this EMF as a voltage or induce voltage. I teach you this thing in the previous class also. Induce voltage, and that is why we use galvanometer. I don't use any particular ammeter whenever we, because galvanometer can be converted into voltmeter, it can be converted into ammeter. It's my choice what particular thing I want to observe. And the sensitivity is very high. Clear? Good. So now if it is a voltage, then everything is easy. Using Ohm's law, V equals to IR, you can find it everything. The main thing is understanding this till. After this, everything is easy. Okay, don't confuse this small e as a electronic charge. So if the coil be closed and total resistance of its circuit be R, then induced current in the circuit is I, which is V by R, E by R here, N by R, del phi by del T. Why should I care here? What I'm saying, care here. Why should not I care the negative sign here? Wow, what a rhyme. Okay, why? Because I is scalar. I don't need to know the negative or positive. In general, I is a scalar thing. Obviously, we talk about direction of a current. Now you are thinking, sir, are so manipulative. Sir, change its dimension according to its width. Right? I am not doing this. We just trying to prove that the energy conservation, nothing more than that. Current direction is never ever necessary. Sometimes it is, like in this case. So I is a scalar thing. I can skip that. If you don't want to skip, don't do that. I, which is V by R, E by R. E is what? Minus d phi by dt. Cool enough. 1 by R minus N d phi by dt. But I don't want this. Now I don't need this. Isn't it? Because I apply a mode. So anything inside a mode, modulus, it is going to be positive. I use maths here because we have a tool to clear it out. Okay. And physics I already teach. This negative sign, why it is important. So it is clear from this equation the induced current in the circuit depends on the resistance, where the induced EMF independent of resistance it is going to be. So I write it down two formulas here, and both of the formulas are important. Formula number 1 and formula number 2, very, very important. Okay. Based on this formula, we're going to derive a little bit more, like power and so and so. Clear? Very easy then. If you understood I induced, so power equals to VI, power equals to V square by R. Heat energy you can also find I square RT. So many things you can find. So induce current and induced charge. Now induced charge we need to know. Okay, fair enough. So as we know, charge is, or current in general, I equals to Q by T. Or in some sense we say change in charge, or you can say flow of charge per unit time, del Q by del T, or sometimes I write dQ by dt. So from this particular formula, I can find induced charge also. So the charge flow through the circuit in time interval del T. Q. Del T. Okay, this I need to. Sometimes small comma can do a major thing. I think that what this particular formula is. Then this del Q equals to I into del T. Fair enough. Put it. Do this, and there is another formula number 3. This is your formula number 3. Clear? Important one. Choosing color for here for me is the most difficult task I can feel. Different colors. Okay. So charge, or this is your induced charge. What it is? Induced charge. Very, very important I'm writing here. Because it is going to be okay. And then you are not aware of induced current. It's a long way back, but you are not aware at that particular moment. You are not remember, or not, you are not, I mean, if you are not clear the concept right now, then I'm saying this line. If concept is clear, then very easy. If you try to learn this, so believe me, then you at that particular moment when 11 done, 12 done, or all 12th done, what is EMI? So if you don't remember EMI in general, so induced current is the second thing, secondary, very last. Okay. So the induced charge does not, obviously it is not going to be. Because del phi, I mean del T is going to be cancelled, N by R del phi. Change on the magnetic flux. So whether the change in magnetic flux be rapid or slow, the charge is going to be in the circuit remains same. This is very impactful statement here. Q induced. Okay, I'm going to write in for induced since now. N by R del phi by del T into del T. Del T cancel each other. So what it becomes? Q induced IN, and if I put N equals to 1, but I don't, N by R del phi. So now from this particular formula number 4, okay, you can see that directly my charge induced is directly proportional to the change of magnetic flux only and only. It doesn't require the time. Clear? The more magnetic flux is going to be changed within the time period, the more charge induced is going to be. The more charge induced is going to be, the more current is going to be. Clear na this thing? you don't get this question in your head, sir, charge induced means. I mean, I want to ask you then, what is the meaning of charge induced? Charge is going to generate or what? What is this meaning? Induction of charge. Before this is chargeless. Tell me. Now you tell me. I asked this thing to you. I mean, if it is a conductor, so it is going to be of lots of charge. Why should I say induced charge? Before it is a chargeless. How much you understand it? So charge induction means at one particular point in a conductor, the amount of the amount of charge is going to be high. At particular point, it is going to be charge is transferred by no beta, not induction and conduction. I'm saying here, it is not transferred. It is just induced. Induced means there is a wire. Obviously, if it is a metal or a conductor, I have so many charge in this in a balanced form. I just imbalance it. Charging an object with induction process. I know, beta. I'm asking what is the meaning here of charging an object without touching it. You can say that, but the general thing is this is a wire having lots of charge, imbalancing of charge. So at one particular point, I have suppose if the current is flowing in this direction. So obviously my electrons flow in this direction. So if electrons flow in this direction, okay, so there the accumulation means I don't know accumulation means. You think in your word, in your sense. Accumulation of charge is going to be more here. Means the electric charge is more in number here. Okay. Is this clear? The imbalance of charge is going to be, and the accumulation of charge, I mean the presence of negative charge at this particular point is going to be extra, a little bit more as compared to this particular point. That is the induction of charge, induced charge. Clear na? Imbalance is not a correct word because the accumulation is the correct, because if it is accumulate here, so they need to flow to maintain that balance once again. And when they mean to flow, they need to do some work or energy or so and so in the opposite sense of what we are doing. Clear? Understand in this way. If someone is slap you once only, you took it's okay. Your friend, okay, no unknown, but a friend. That friend is slap you once again, okay. But in a third time you slap it in a backward. No. Yadira say no. No, beta, it is a human tendency. If no, you are saying change your perspective. Because Gandhiji also tell if someone slap you on your one cheek or a one side of a face, so put it in the second. After second, they don't tell. So I tell you guys, do this. I mean, that is a human tendency. I'm saying that. So the same thing is happening here. Okay. If there is an accumulation of charge is going to be here, so this charge need to flow in this direction. So current is flowing in this direction in the opposite of this. Okay. Learn concept. Still learn concept there. Okay, I need a break right now. More talking. I did with you guys only 12 pages. I need to teach you approx 50 today. So be ready to be with me till 9:35 or at least 40. No, I'm not taking a time more. But I'll need here 5-10 minutes extra. Not 10, minimum 5. Okay, so I'm not leaving, I'm giving a break here again. And not 10 minutes today because I already eaten up 5. So 5 minutes break because after that our bullet train of teaching is going to be starts. So yes, beta, ask Vishwanath. whatever. Ask me quickly, beta. It's already. Ah, okay, I write it down 5. You can take 10. Okay, 5 to 10 minutes. Go ahead. Hello, hello, hello. Hello, 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 hello. Are you there, guys? Okay, so let's do this thing a little bit more quicker way. Now the more understanding part, or you can say explaining part is done. Formulation is remaining. Our motional EMF formula is going to be BLV. I'm going to use the, I'm going you, what I'm saying. I'm giving you a hint here, going you saying, what happens to me today? I'm giving you a hint of a formula, BLV, transformer formula going, EMF we're going to discuss also, and another important aspects or formulas. Okay. Okay, so motion of a wire in a magnetic field, it generates induced current, it generates induced charge, it generates field, it generates power, energy, and so and so. Okay, every particular little, big, small thing is related to EMI or the concept of electromagnetic induction. Nothing more than that. So motion of a wire in a magnetic field. What happen? if you move your wire or a conductor, take a wire as a conductor also, in a magnetic field. So motion of a wire through a magnetic field causes a separation of positive and negative charge. Separation of positive negative charge means induction of charge. This is the meaning of induced charge. Okay, so that end become positively charged and one end okay, so that one end become positively charged and another end becomes negatively charged. Is this clear? And that is the induction. This particular thing is induction. Induced charge. Induction of charge. Induction of charge due to EMI. Is this clear, everyone? Due to EMI. Turn on your cameras, everyone, and is this clear? Good. Okay. Huh. Is this clear now? So based on that, we have some figure shows the wire. I mean, previous figure we are talking right now. Figure shows the wire enlarged to some extent with some of its positive and negative charges. Fair enough. As the wire moves towards the right with velocity v, charges within a wire have its velocity you can say superposed on any other motion they have within the wire. Let direction of B is perpendicular to the plane of this particular plane, I mean out of the plane of paper. If a charge Q moving through with some velocity V in a magnetic flux density B, so the force on this particular F equals to QVB. We already understood this thing. So what it states that, let's quickly do this thing. So as we can see, yeah, the motion of this particular wire in this direction, right? V. Charge is going to be accumulates in this, and this dot explain you the direction of a magnetic field. It is a plane of paper. This is paper outside the direction. So that is force, or you can say magnetic force, equals to QVB. Why so? Directly I am writing this because we know this. Magnetic force is a vector quantity, so charge is a scalar thing. And V cross B, that is your thing, na? But magnetic field outer the plane of paper in the positive z direction, or you can say positive z direction, or your motion of this particular wire is in the right hand side. So the angle between this V and B, or you can say theta between V, theta here is 90 degree, as simple as that. Is this clear to each and everyone? Clear na? Why should I write directly QVB? Maybe some of you think like we don't have this direct formula. Obviously we don't have, but due to the angle thing or due to the direction between these two, both of them, the magnetic field and the movement in this wire is perpendicular to each other. So we can write directly. Now the force F is at right angle to both B and V. Fair enough. We know this thing again. Fm, which is a vector thing, its direction if I'm going to write, which is QVB in this way, QVB sine theta n. So because this n is direction of a force is going to be perpendicular to V and B both. Clear? This is very important thing and I give you so many times. Okay, in any particular vector product, if the third vector is going to be the perpendicular to the both the vectors, so it is going to along the length of wire. Obviously, it is going to along the length of wire directed from A to C. The negative charge. I mean, they just explain you with the terminology of force how it is going to be. Very easy, very simple. Here we can discuss. This is your one axis. This is your another axis, and this is your third axis. So in this third axis, my magnetic flux is going to be as simple as that. In this particular axis, my velocity is going to be. So obviously the third axis, which is perpendicular to the already both the axis, in this direction force is going to be, and due to this force there is a induction of charge. Is this clear? So if you're thinking why induction of charge, so why answer is this. Clear? The answer of your why is this. So there will thus be relative motion momentarily of the negative with respect to the positive. Obviously then due to this force, uh, the negative charge tends to move in one side, and positive charge tends to move another side. And then there is a force now. Electrostatic force. Clear? So due to this force, due to this magnetic force, the accumulation of charge is going to be separated. As you can see in this, the charge is positive, negative, positive, negative. Okay, you can see this one is your positive, this one is your negative, this one is your again negative, positive, then negative, and then positive. But here we have all positive below and all negative upper. So that is your induction of charge. Again I am writing Q induction. Q induction means charge induction. Clear? So that is the reason. Moving ahead, now I can find the everything like potential difference or electric field. When I have the potential difference, so I have an electric field also, isn't it? Because this potential difference is nothing but EMF. So when I have this or this, you can say potential difference. So I have electric field. Is this clear, everyone? And that is clearly written over here. I'm not saying anything what is not written. Hence, an electric potential difference V is induced between the ends of the wire, obviously, due to which electric field E is created. Obviously, E equals to V by L. If it is a wire of length L, okay, understood in this way. If it is a wire of length L and there is a potential difference in between this of this particular wire, and the potential difference is this, V equals to E equals to minus N dF by dt. So due to this potential difference, there is a electric field also. So this is your induced electric field. E equals to E by L, or E equals to V by L first of all, and that is going to be E by L. In general, I hope and believe you know from where this coming, this relation V by L, because we have this general relation, electric field equals to minus dV by dr. So for greater length, I can write minus V by L, and I skip the negative sign again. Why so? Because V is a potential, L is a potential, but electric field is not. So how can I do that? I can do that because this negative sign again tells me here the direction is in the opposite direction. Nothing more than that. Clear? Who is calling me right now? Understood this point? Wait for a while, but I need to take this. Is this clear? So obviously when we have electric field, so the direction E is from from positive charge to C to A, and now what is C to A? They stick to this particular C to A. So if the direction of electric field, obviously if it is a positive and it is a negative, so better direction of your electric field is in this way. Okay. Wait, I make it and then I take a screenshot. This is the best thing. This is screenshot. Don't. Why this window is not coming? Seriously? Then I can do this. Copy. Then I can do that. Is this clear? Huh. Clear? So here the direction of electric field is this. Is this clear now, everyone? Good. So when the direction of electric field is this, so it again proves the direction of electric field and the direction of force are the same thing. The force is going to be in the upward direction. So obviously because of force direction we can find this. Okay, so now motion of a wire in electric field, continuity thing, F equals to Fm. So directly from here you can find it down. And that is your origin of EM waves, or this particular important relation I am writing when we are going to discuss here. So in this condition, obviously due to this condition, my electric force is equal to the magnetic force. So my magnetic force equals to QVB, my electric force equals to QE in general. So E equals to VB. That is your one of the important, or I can write very important relation, and that is the birthplace or origin of your EM waves or electromagnetic radiation. The simple thing in a light, I mean, how we can prove the light is made up of electromagnetic field or electric field or magnetic field? I can change this with C, simple, isn't it? I can do that. My light is made up of this, E equals to CB, where C is the speed of light. We're going to prove that, don't worry. I'm not writing just randomly. Till now you understood everything. E equals to VB. There is an important relation, more important in the, you can say, chapter EM waves or electromagnetic induction. Electromagnetic induction we are doing basically. Okay. Is this clear now? So this we're going to use. So induced potential difference between the ends of the wire equals to E equals to BLV, and that is your known as motional EMF. Now coming back to this picture, if this is my E, which is electric field, I can write, I am going to write with this symbol. I love this symbol, E, induced EMF by L. So that is VB. So how can I do this? This is known as motional EMF. Motional EMF means due to the motion of what? Conductor or a wire. BLV. In great detail we are going to discuss also, but right now this is one thing. Is this clear, everyone? Or you guys need a quick recap? Okay, going back to the initial. This thing is clear. I is this before. Okay, charge is clear. Okay, so what happening here? Again, in a quick way. Recap. Motion of a wire in a magnetic field means there is a magnetic field in this way, or you try, I mean, there is a magnetic field in this way. Again, assume this particular as a, I mean, pen of mine as a wire. So if I move this wire in this way, okay, horizontally, and the magnetic field is in Z direction. So in Y direction, your force is going to be, that is one thing apply due to the magnetic force, which is QVB, because this particular conductor having a charge particle, charge accumulation. So due to this magnetic force, there is an induction of charge is going to be due to EMI, first of all. And induced charge is going to be generated because of force. Which force? Magnetic force. So if there is a charge induction is going to be, so there is an electric field is going to be, obviously, fair enough. So this magnetic field, this electric field is going to be equal, and this electric field is nothing but your EMF, or you can say induced EMF by length. Okay, so due to this electric field, I have electric force, electrostatic force Fe, which is equal to the magnetic force Fm, which is QE equals to QVB. So E equals to VB, and then E equals to EMF, which is also known as motional EMF or induced EMF, because of motion of wire. That is why I said motional EMF. This symbol, or you can write small e also, BLV. Is this clear, everyone? Clear now? What is happening here? Due to the motion of, either you can understand a coil, or simple wire. In simple wires it is going to be generated. There is no need to take a coil always. That is the main thing here, stating this everything. Is this clear, beta? Good. Moving ahead. So this is, we already done this thing. We're going to formulate it. I mean, we already understood. We're just going to formulate this thing. So motion, motion of a wire in a magnetic field. In using this equation, it must be remembered that B, L, and V are considered to be perpendicular one another. Very good thing written in a very first page of this particular concept. Like magnetic field is in this direction, fair enough. Or this velocity is in this direction, good. So these are perpendicular, and this length is this. So this is your L sine theta. So obviously L sine theta, if I draw here, so this is in this direction. So you can see that L sine theta, B and V are in perpendicular direction. Is this clear, beta, everyone? So if they are not, then only the component, means it is stating again, if they are not, only those that are mutually perpendicular are to be considered in this case of induced EMF, which is minus BLV or minus LV cross B. Means if it is not perpendicular, this is your initial case, na? Initial case is this. It is not perpendicular. Okay. We need to take then this, which is the perpendicular. Second case, secondary case. We are not considering this first case then. Is this clear, bit everyone? So induced EMF is going to be, you can say L V cross B, and V cross B gives you obviously BLV. Simple thing. Okay. This formula. This formula, induced EMF equals to minus L. I mean L now I am taking as a vector because of this theta component, and V, L you can say dot V cross B. So simply V cross B is in this perpendicular direction, fair enough. So then L dot V cross B, VB, N, and this particular N is in the same direction with L. So due to this, minus sign taking, equals to minus L BV, L BV, and BLV. I mean, I like to pronunciate and write in this way. Simpler looking, for me at least. Okay, you can write in your own choice, but that is simple. BLV. Clear? Good. Moving ahead. Now, this is everything. Just extra things. In a particular case, if B and V are mutually perpendicular and L makes an angle theta with B, okay, see this, then this magnitude EMF is E BLV sine theta. Special note, if any one of these V parallel B, L parallel B, this, then induced EMF going to be 0. Obviously, simple thing it is necessary, but special note again, good one. So as we know, induced EMF equals to minus L V cross B. So if in this particular scenario, V can be parallel to this, L can be parallel to B, or L can be parallel to V. In all the scenarios, this is going to be 0. Okay, is this clear, everyone? In all the scenarios, this can be 0. Clear? Should I move ahead? Now this is the few points. The main thing we done. What is electromagnetic induction? Oh, nice. It is phenomena of production of induced EMF due to a change. I don't know what it is why it is mentioned. Let's revise this. If it is due to a change of magnetic flux, number of magnetic field lines connected to a closed circuit called electromagnetic, explained by two cases. Okay, let's see that. Case 1. Okay. So let's revise this. Case 1, the motion of a magnet increases. Okay, the motion of a magnet increases the flux through the coil, and flux will be generated in the opposite direction by the induced current. Clear enough? Second experiment, the motion of the magnet decreases through the coil, the flux is generated in the same direction by the induced current, hence opposing the increasing flux. Fair enough. Lenz law and okay, and law of conservation. So basically, it just share us with the law of conservation of energy. Oh my goodness! After that much, you have first. I mean, you. What I'm saying, you get your first question. Do this. It is your assisted practice. Okay, I'll explain you what happening here. A horizontal telegraph wire. So it is length. Not need to explain. Meter. Oriented along a magnetic east-west direction. Direction is giving. Freely falls freely under the gravity from a height of 10 meter. Okay. Find the EMF induced in the wire at the instant the wire strikes ground. BH is given. G is given. Do a little bit calculation. Think which particular formula we need to use, and then find EMF. As simple as that. Clear? S is given. Think a little bit about what? Equation of motion to get V, and why you need to get V? To find the speed of, I mean, to find the speed in general. To use the formula BLV. B you can take H, BH in general. L is given, if I'm not wrong. Yeah. So the main thing is here you need to find V only. How are you going to find? S is also given. S is H here. Okay. One simple hint. Hint. Use kinematics. Use EOM, equation of motion. S, which is H, if I'm not wrong, is given. Or a horizontal telegraph wire, a magnetic this, free fall. In free fall, initial velocity 0. This is the case of free fall now. You're dropping something. What I'm doing. Clear? So with this you can find V, L you have, B, take as a BH directly, and then use the relation, simple, BLV, and find this and tell me the answer within 2 minutes. I don't have, I mean, I don't have more time to give you. Tell me the induced EMF in the wire. Very easy, very basic. I don't think you guys need more explanation on this. Okay, let's. Okay, now the important formulas related to BLV is going to be given. Oh my. And then there is a energy also. Okay. And then we are done. Yeah. So we can take time. But I want to teach you transformer EMF also. So I need quite a bit time. So I'm stealing your time. Do this quickly. That is very easy. Tell me the correct answer. Yadira, what I'm saying. Yadira, you are in the booster batch, na beta?
Sir, am I audible?
Yes, you are.
Yes, sir, I'm there, sir.
Okay. So you prepared enough? I mean, because you need to be prepared also for
Sir,
your first
preparation is
lecture.
going side by sides.
Huh?
Preparation is going side by sides.
Good. And what other students? Sudarshan, are you also?
Oh, sir.
In the present, how many of you? Only one. Yajira is there. There is Shashidharan or something, another name I don't remember right now. Muthukumaran is there. Or Yajira is there. I remember too. Maybe Jyotsna also is there. No, Jyotsna is not. Okay. Okay. Okay, tell me the answer. Sai. Oh, nice. So are you prepared enough? You hope so. Okay. Tomorrow is your chemistry lecture, if I'm not wrong, with the JEE booster batch. Okay, just one hint. Which particular? I'm not going to teach you the booster batch. One revealing thing. You don't need to face me there. Or one important thing, whatever the particular subject topic, the number of questions is going to be assigned to you guys. Obviously, we assign few questions. So then you need to Vishnu, Muttu, Sakti, Sai. Okay. So Vishnu is not there. Sakti was present in the last class. I don't know he or she. And then Sai is there also. Good. Hmm. What is the answer, beta? See, I mean, in this way, they ask question, combining the two concepts all together, and then leave on you guys. Use your brain, understand which particular formula you're going to apply. No one is going to give you a hint, and that's why I say so many times, do a quiet number of practice, practice, practice. Okay, you take so much time. I don't have. U equals to 0, A equals to minus G, obviously S equals to minus 10. What is the meaning? Understood in this way. Suppose there is a magnetic field. Sometimes I'm drawing so bad. In this magnetic field, now understand another thing also. There is a wire. Okay, another color. There is a wire is going to be fall in this way. There is a wire is going to be fall. Okay, obviously free fall. So A equals to G. Initially U equals to 0 and S, the height is given from which particular height is minus 10 meter, because everything is in the negative y direction. It is x, is x, y prime, which is negative 5, y and x prime. Clear? Now let the speed of the wire at last moment, because I need to find the EMF at last moment when it is passed through this. V square equals to 0, or you can say simply equation of motion. I think it is given also. Still I am rewriting this thing. 2AS. So from here you can get V 196 14, and I mean V square equals to 196 meter per second square, if I'm not wrong. I mean meter square per second square. Then V is this, and then simple induced EMF is BHLV. Put everything, and the answer is 3 into 10 to the power minus 3 volt. Is this clear, everyone? I don't think there is any further explanation is need to be. Clear? Clear na beta? Tell me quickly and turn on your cameras too, yaar. Everyone. Good. Is this clear? Good. Do this. A conductor of length this is moves parallel to itself, okay, with a speed of this at a right angle to a uniform magnetic induction this. What is induced EMF? Tell me which, I mean, tell me the answer. The same thing you need to use. Uh, if you are confusing in the sign convention, so don't, because V is perpendicular to B. It is given. Everything is given then. L is 10 centimeter, 0.1. V is this, B is this, induced EMF, BLV directly. 1 into 10 to the power minus 4. Exactly. Okay. You can write in this way also, 100 microvolt. If you don't, yeah, 10 to the power minus 4 or 100 microvolt. The same thing, na? 100 into 10 to the power minus 6, 10 to the power minus 4. Clear? Or 0.1 m. M means milli. So many things you can write it down. To 10 to the power, because minus 4 is not something. So two ways to write this, E equals to 0.1 millivolt or either this. It's your choice which particular thing you pick. Okay, good. Now this is motional EMF. We already done this thing, so I'm going to quickly recap this thing for you guys. Whatever the important formulation is still there, we're going to spend a time on that. And then there is something not given in this thing, but I feel that is important for you guys. If it is omitted, I'm saying this line again. Listen this. If it is omitted from your any particular, you can say JEE syllabus or CBSE syllabus, still you need to know this thing. What I'm going to tell you. Transformer EMF. Okay. I know transformer EMF is given in this as a proper thing, but I'm going to teach you. So let's do this. So what exactly the external mechanism that maintains the electric field in the loop to drive the current, or what is the mechanism to produce, and that is your motional EMF. We know this thing, so let's do this quickly. Motional EMF, the magnetic flux B dot ds can be changed by keeping the magnetic field constant as time passes and the moving the whole part of the loop, keeping the loop at a rest and changing the magnetic field. So there are two ways. Read this line after the lecture again. I'm doing a little bit quick way, but that is important also. Okay, listen this. There are two ways to get the EMF. Simple, the relative motion. So it's my choice. Either I can move the conductor or either I can move the magnetic field. This is written over here. Or the combination of both. Clear? Is this clear na? So there are three ways. Either I can change the magnetic field. How so? Changing the magnet. Either I can change the wire. Obviously, changing wire means, or you can say moving wire, not changing wire. Moving wire means moving conductor or coil or simultaneously. I mean, this is going in this way and this is going up or down. Okay. See, this is locomotive response. I cannot do this thing or this thing all together. Try this after the class, not right now. Okay. The magnetic flux phi equals to B dot ds can be changed by this. Why magnetic flux is changing? Because of changing, getting induced EMF. So combination of both of them. So motional EMF is what? At t equals to 0, the free electrons of the wire also move with this velocity v together with the random velocity they have in the road. Means if you move a conductor with some, so the electrons is also moving with this. Thus the magnetic field exerts an average force Fb, which is q v cross b. Fair enough. Where the charge q is assumed 1.6 into 10 to the power minus 19 coulomb if we consider q as an electron. Okay, the magnitude of force remains the same, but the direction of reverse due to the negative charge in the electron. Cool. Now this field exerts the electrostatic force also, QE. Again good. The charge keeps on the accumulating. Now the main thing coming here, what we already done. I mean, this is the accumulation of charge, or basically you can say that this is the induction of charge is going to be happening, and that FB, which is Fm back then, is going to be here. Same thing we are writing QVB, QV cross B equals to QE. I put the mode just to get rid of negative sign. So V equals to BE, fair enough. After this, there is no resultant force on the free electrons of the wire PQ. The potential difference between the two ends Q and P is V, which is EL, BLV, and this EMF is going to be motional EMF. I already teach you this thing, so that's why I'm doing a little bit quick. Okay, motional EMF is nothing but BLV. I write this way. You can write VBL or any particular. It's your choice. Clear? The same thing we are doing till now. The method or the terminology is changed. Just so motional EMF we already know. Now this is the main thing. This diagram you can see so many times in a question. From this diagram I can explain you again what is happening, and then we rewrite this formula. So what happened? There is a magnetic field already in the existence. Now you tell me where in this particular diagram the direction of magnetic field is. Tell me. What is this cross represents, you guys? What is this meaning? Tell me, beta. Arre? Is this that much hard? Okay. You are saying something I didn't get, you guys. What is that? Represent. I mean, again I am refreshing. I am done now. Tell me, beta. Magnetic field lines going inside the surface. Exactly. This is inside the surface or into the plane of paper, or that is outside the surface, outward, inward, into the plane of paper, outward. Okay. So if it is inward only, if it is inward, and this is my length of a wire, this is the length. Okay. And in this particular coil, I mean, there is a wire, I mean, there are two wires. One wire I am moving with L length, and one to complete a circuit. This wire is just to complete a circuit, this particular thing. Don't confuse here. This wire is to complete a circuit. In this particular wire, I apply a resistance also to make a circuit complete. Clear? So the moment I move this particular wire in this way, okay, I can change the color now. If I move this particular wire in this way, so there is an induced EMF is going to be generated. Fair enough, clear enough, we learn this thing. And if it is BLV, beta, okay, in this particular, now in this particular circuit, figure, we can say B, we can write directly circuit. So in this circuit, what is going to happen? Current I. If R is the resistance of the circuit, okay, fair enough, then the current in the circuit I, E by R, EMF by resistance, or you can say potential by resistance, BLV by R. Clear? So I, now if in the figure, I mean in this particular figure, in the B circuit, there is small r also. So in the given figure, we can replace a moving rod AB by a battery of EMF BLV. Okay, do that with a positive terminal at A, or where is A? Here is positive terminal. So I can write A or B again. Here is my positive terminal, here is my negative terminal. Okay. Positive negative of the rod may be treated as the internal resistance of the battery. So this R is treated as a internal resistance. So the net current I equals to E R by R, capital R, which is resistance of a wire, small r treated as a EMF. I mean treated as a potential difference or a battery due to EMF, due to this. So this I becomes BLV R by R. Is this clear, everyone? This is clear na? Is this clear? Nothing I'm doing new. Just I'm moving my wire which generating a EMF, and that EMF is treated as a potential difference or a battery. Due to this battery I can make another resistance R, and then this is going to be the scenario. Good. Now inductance and energy transfer. Okay. Let's complete this, or should I teach you transformer? Okay, I first of all want to teach you transformer, then we focus on this. So this is clearly understood what is motional EMF and what is the induced current due to the motional EMF, because this particular formula is going to help you out, and that is a very important formula also. So sometimes directly they want to ask either this potential difference directly, either the I or either this small r also. Okay, given everything and then small r. So you need to focus on this formula. Okay, wait. Hello, there is a message from Ankur sir side and pass on to the your friends in the groups. Mole concept you need to go through once. Okay, he going to teach you something related to mole concept. Maybe stoichiometry something. I don't know the name exactly, but the main thing is mole concept. Clear? Okay, good. So back to the basics and sorry, back to the business. This is one of the kind of a EMF. Maybe, sir, it is not related to you. Oh, Pariksha sir, you are asking about the topic. Sorry, I thought you'd want to know about this mole. Okay, see, we already understood the emotional EMF. I mean, this BLV and this EMF concept. So instead of simple thing, I make a circuit. I make a wire. I apply a resistance in this, and I connect another wire on this and try to move. I mean, starts moving this. So due to the motion of this particular wire, which is this wire. Okay, wait. Maybe you are confused which particular wire I'm talking right now. This wire. This is the wire. I move in this wire in this way. Okay, in this way. So due to the motion, there is a EMF is going to be generated as a voltage BLV. So there is a current is going to be in this circuit. Now due to this generated EMF, I can take this EMF as a my potential difference as a cell, as a battery. So whenever there is a cell or there is a battery, there is an internal resistance also. So I assume or I make this small r as an internal resistance of this particular cell due to the induced EMF. Is this clear now? Okay. Okay. Now the main thing is what I'm going to teach you. Just give me a minute. That is your transformer EMF. Very easy. You don't need to worry about it. What is going on here? Uh, but you need to look for a. I mean, wait for a while. Okay, if it is copy image, if it is going to be copy, so let's do this. Yeah, perfect. Then my job is done. Okay, so this is your transformer EMF. Important one. Transformer EMF, because you need to understood, and because if there is a question going to be on this particular point, so at least you know what is going on here. So see, as in simple motional EMF, there are two types of EMF in general. First of all, motional due to the motion of a wire or a conductor. Transformer due to this transformer effect. What is a transformer? You know, maybe. Tell me, anyone. Transformer is a device in which we have a two currents, or sorry, in which we have a two coils, primary coil and a secondary coil. Okay. So if we have a sinusoidal AC voltage, then the magnetic flux is phi m sin omega t. Uh, wait. Fair enough. Because if I'm going to write now, then it is going to be, I need to write control Z. What is happening here? Just a minute. Why this is not working? Just a minute. Stay there. snip tool, because that is going to be helpful for both of us. Yeah, now I can use this is because if I'm going to write now, that is take a little bit more time. Yeah, now I can do this. Is this clearly visible? Mm, yeah. Okay. So what we are doing here for electrical transformer, what is a transformer? The EMF equation is a mathematical expression used to find the magnitude of induced EMF. What is happening here in general? Due to this, if I apply a current in this particular, okay, suppose what is happening here, very easy, very basic. There is a one coil. In this particular coil, I apply this VI, potential difference, initial potential difference, VI. So when I apply potential difference, so due to this current, this coil behave as a magnet or a temporary magnet. The moment till I apply the current. Clear? Clear enough, everyone? Is this clear? So this coil behave as a temporary magnet, and this temporary magnet generates a magnetic field. This magnetic field passes through this coil. As you can see this dotted line, this magnetic field passes through this. So due to the motion of this magnetic field in this coil, there is a generation of induced EMF, which is known as E2. And due to this EMF, which is generated due to the flow of this particular uh, magnetic field in this particular coil, secondary coil, there is a current also, E2. And this particular induced EMF E2 we can take as a V2, potential difference. Same in the previous story. Clear? Instead of moving magnet or coil, now what we are doing, we apply a alternating source to the coil. This alternating source, AC current in general, uh, this alternating current or AC current or simple current generates a magnetic field in a particular coil. So whenever a magnetic field, so in the surrounding, there is a, if okay, understand in this way, if it is north, it is south. So what is going to happen then? This magnetic field is going to, obviously the power is very high, so the magnetic field is going to in this way, north, south, north, south. Mhm. In this class, I can, yeah, look like a butterfly. See, I need to do so many efforts for you guys. Okay, look. So in this way, what is happening here, whenever I apply a current in this, so there is a magnetic field going to be, and whenever there is a magnetic field, north, south, it becomes. So there is a flux passing through this, and whenever a flux passing through this, I repeat, I apply a alternating source, or you can say alternating current carrying source or AC voltage. So for electrical transformer, the EMF equation is a mathematical expression used to find the this magnitude of the EMF in the winding of the transformer. Now consider a transformer as shown in the figure. N1 and N2 are the number of turns. Primary and secondary wings. Okay. When we apply alternating voltage, beta, I repeat my word, alternating voltage, because we have alternating current, so we have alternating voltage also. Okay. Arrow direction, wrong sir. Which particular arrow? हाँ बेटा, you are considering about arrow direction here. I need to draw this in 7 times. Now it is correct. Arrow direction, yeah, focusing. Okay, it's okay. Uh, Alternating voltage V1 of frequency F, the primary winding, then alternating magnetic flux F is produced by the primary winding. So in general, in simple case statement, what is happening here? Due to alternating, due to alter, due to alternating source or due to alternating voltage. Okay, there is a magnetic flux is going to be generated, and that is in primary. F equals to Fm sine omega t. Clear? And why this omega? And what is this omega? Omega equals to 2 pi f. Frequency of the alternating source. Is this clear, everyone? Is this clear now? Is this clear? So what is happening here? There is a induced EMF is going to be generated in the primary winding. It is going to be E1 minus N1 d phi by dt. Clear? And in secondary, it is going to be wait. And with the power equivalence thing, okay. So there is a, due to this phi, which is phi b sine omega t, okay, sine omega t. So induced EMF is going to be generated, obviously in N1. So E1 equals to minus N del phi 1 by del phi t. This is your phi 1, phi 1. So that is going to be how much? Minus of phi b n d by dt of sine omega t. Sine omega t. So this phi 1 is going to be minus n phi b omega, minus minus cancel each out, cos omega t. Okay. Is this clear? Now this is your voltage for EMF voltage or induced EMF voltage for 1. For 1. I am repeating my sentence, for 1, not for second. But we know due to this power relation, power is going to be equal in both. Isn't it? Power is going to be related in both in transformer or what? And I mean, what this particular power, if I'm not wrong, we have this formula, na? N1 or P1 equals to N2 P2, which is N1 V1 equals to VI. N1 V1 I1 equals to N2 V2 I2. Okay, so from this particular relation we can find the power or induced EMF in the second also. So that is the main thing. Maybe this relation, last relation is going to be wrong. Maybe I'm not sure right now. Okay, check this. But the main thing is the the main thing is this relation. This one. Is this clear, everyone? Due to alternating voltage of frequency F, there is a magnetic flux is going to be generated phi 1 in primary coil, phi b sine omega t or phi naught sine omega t. Due to this magnetic flux in this particular coil itself, okay, in this particular coil itself, there is a EMF going to be generated. Sorry, minus n d phi 1 by dt. And when this flux is going to be passes through this, so and then again there is a magnetic field or a magnetic flux is going to be generated. Clear? Clear, everyone? This particular generation of EMF due to the transformer effect is known as transformer EMF. Clear? Simply you can understand in this way, there is a magnetic flux is going to be passes through, this becomes a magnet, and when the magnetic flux of this is passing through this, so directly N2 d phi by 1. So from here you can get the formula also. Clear? N2, why should I write? Because I'm talking now about this. Flux is only and only generated for this. It doesn't have its flux of on isn't it? Because you don't apply any particular battery here in this side. So flux is because of this primary coil. So either in the flux of primary coil or either in the flux of secondary coil, that is the flux. Sorry, that is the EMF. Clear? You just need to change the number of turns. D phi B omega cos omega t is going to be still there. Clear everyone? Good. So that is the important thing. Okay. So that is, now we talk about inductance and energy transfer, and that is going to be very, very helpful for you guys in AC, alternating current, which is the next chapter. So let's see what it is. Introduction and energy transfer. In the given figure, if you move a conductor AB, okay, what is a conductor? This is my conductor. Conductor, a simple a wire or a length or a conductor of length L. This is my conductor A. This is my conductor A and B. Okay. If you move in the given figure shown, if you move the conductor AB with a constant velocity V, then the current in the circuit is going to be I equals to BLV by R if R is 0. Fair enough? We understood this thing? Clear? Now a magnetic force is going to be IBL. Obviously, in this particular circuit or in this particular conductor itself, AB, there is a magnetic force. IBL sin theta or IBL simply. So this is your, putting the value of I, you can get this B square L square V upon R. Clear? This one till now? Everything clear to each and every here? Clear na? Good. So this is my, due to this induced EMF, due to this induced current, there is a itself a magnetic force is going to be generated. Why so? Because everything, this current is generating and flowing in a existing magnetic field. So whenever there is a current in an existing magnetic field going to be passes through, so there is a magnetic force is going to be generated, and this is my magnetic force. Putting value of I B upon R, we can get Fm magnetic force B square L square V by R. Simple, fair enough till now. Good. So to move the conductor with a constant velocity, what I'm saying, so to move the conductor with a constant velocity V, an equal and opposite force F to be applied in the conductor. Now what is this? If it is a force in this particular sense, you can see that there is an arrow also Fm, but I need to move in this way, so I need to apply some force on this particular conductor. Clear? Because it is, I mean, this magnetic force pulls this conductor in the backward side. So thus F equals to Fm, I mean at least this much force I need to apply. So the rate at which work is done by apply the applied force, that is P applied, force into velocity. Now this relation of work done is very easy, beta. I mean power equals to work done on time taken. Work done is beta. Work force into displacement upon time. Displacement upon time is nothing but force into velocity. So there is this relation also, force into velocity of power also. Understood? Power is nothing but how much work you, I mean how much you are able to do work in a particular time unit, work done upon time. Work done is nothing, force upon displacement upon time, displacement upon time, velocity, Fv. So you don't need to worry from this, I mean from where we get this relation. I proved this already. Clear? So we need to apply a force or we need to apply a power in opposite of this particular magnetic force. And how much power you need to apply? This much. And if you have a power, okay, so then the dissipation energy is going to be then, because power is how much energy is going to apply to generate or to do that particular work in a continuous way. Clear? Okay, this is 9th, 11th class thing. If we have a power, so to maintain that power we need to supply a constant energy, and the rate at which energy is dissipated in the circuit, power dissipated, is going to be I square R, which is equal to the power applied. That is going to be this. Is this clear? So here we have two things, power applied, that is FV, that is B square L square V square by R. Very beautiful formula, or very important also. Important. This power applied, whatever the power we applied, this applied power is going to be dissipate, or you can say equal balance in the opposite direction, is going to be dissipate in this resistance with this power dissipated in the resistance of a circuit of resistance R, I square R. We know the value of I. Put it down. The same thing we're going to get. Someone ask me, please. Why don't you ask? If everything is balanced out, then what we are doing here? Tell me. If everything is balancing out, what we are doing here? Here in means in this physical phenomena I'm talking. In class, I'm teaching you, you learning something new. But what is happening here then? Obviously, it is not going to be the almost equal, a little bit lesser. But if there is a formula, or if there is a question, tell me the applied power. What is the applied power? To pull this particular length, to pull this particular conductor of length L. So you need to use this formula. Simple. You have a magnetic field B, you have a length L, you have a you have a velocity V, and then resistance R. B square L square V square by R. But they can ask the same question in reverse way. What is the reverse way? Tell me the power dissipated on this resistance. Okay. In general thing, obviously it is not going to be equal enough, a little bit lesser, but theoretically we assume this. Because theoretically we assume so many things, like there is no loss of energy, there is no mechanical or any other conversion of energy, but it is not going to be. Obviously, if you there is a conductor and you rub this particular conductor, suppose this is a rail of my wire and this is the conductor. If I am going to rub this, so the some energy is going to be dissipated in this form also, frictional also. So many things we are assuming right now. Clear? So formula wise it is equal, but in real sense it is not. That is my meaning of saying that. Okay. We are okay. Do this question and do this a little bit quick because it's already 9:20. After this, we have an energy consideration, that is quantitative. I'm not going to explain much. Already I am doing. And there is qualitative. Qualitative I can that. And then, okay, now it's up to you, beta. If you want to do the CA, do it in quick, a little bit quick. Or what I can do for you guys, I explain you this, and you guys do the class assessment by yours. Tell me what particular deal is easy for you. See, I'm giving you the deal. Sometimes I become so many things instead of being a teacher itself. I am giving a deal as some friend or something. If you pick this, so I can give you this. If you pick this, so I can give you this. Tell me. I want your response, not your black windows. We'll start CA, sir, after this question. No, beta, you don't need to. I'm saying that do these questions quickly, and then in the next 5 minutes I can teach you the energy formula or energy things what already we done, and then you start CA. That's what I am saying. You don't need to start CA just after this. You need to stay 5 minutes more. I am teaching you, so be there. I teach you extra and you don't want to be here at least 5 minutes. Yeah. Okay. See what is written over here? I give you this thing. A rod of PQ of length 1 meter is moving with velocity this at an angle of this from horizontal under the influence of magnetic field this as Okay, calculate EMF generated across the length after the equilibrium state. Now, beta, equilibrium state is very easy. L sine theta you need to apply. As simple as that. That is the equilibrium state. We know that V equals to velocity component minus 5 cos 5 sine. Okay. Why minus 5? Because velocity is in this direction. So cos is going to be the negative x direction and sine is going to be this perpendicular direction, and we need to take care of sine, not cos. Clear? Because magnetic field is in the plane of paper. Cross is plane of paper, beta. So I need to take this sine component. Maybe if I'm not wrong. Huh. Sine component, na? Okay. Okay. So B equals to 8K. Obviously, into the plane of paper, K. L equal, again, L equals to 1 joule. J. In this, there is a J means so many things I need to teach you in a one sentence. One question. Okay, J you consider. This is my V. Okay. So there is one component which is V sine and this is Vx. If I choose this X, so this is going to be negative, this is going to be something perpendicular. Okay, if I X choose this, so then I need to choose a perpendicular like this. This is my Y then, and another perpendicular. This is my Z then, or you can say into the plane of paper. Assume this now. I can't draw everything. Okay, so the third perpendicular side is into the plane of paper. Clear enough? So this L is J. So J means J direction. So we know EMF is nothing but V cross B dot L, or you can write in the reverse way, L V cross B. Put the vector product. This is your vector product since cos 37 and this. Okay, use this. Thus imply that the, okay, we are still on this now. So V cross B, do this positive, I mean this thing. Therefore, the EMF generated PQ is 4 volt. I mean the main thing is this. The vector product you need to understand here, nothing more than that. Clear everyone? Formalize the same thing. B EMF L V B. Simple. This give you some vector thing, and vector into vector it is a what? Scalar thing. And we know potential or a electromotive force. Electromotive force, don't confuse itself that is a force. So it is something vector. No. It is a potential in general. It is a scalar thing. Clear? Okay, don't go with the word always. Word can be anything. Is this clear everyone? So the EMF generated across the rod PQ is 4 volt. Is this clear with everyone? No. Sudarshan, you are saying no or yes? Clear? Good. The same way we have this. A rod of PQ of length 1 meter is moving with velocity this horizontally under the influence of magnetic field of magnitude this. Again, it is in the K direction. Calculate the EMF generated across the length after the equilibrium attained. Same thing. Okay, directly. So the implies, that implies P and Q are equipotential, and we can see that V cross B is a perpendicular to the length of a rod of L. EMF generated 0. Simple. Because I cross K gives me J, and J dot J, then J dot Y. So there is something wrong here. It is going to be, okay, it is I na. L is I. So here it is wrong written. 1I. I think and I believe I dot J equals to J dot K equals to K dot I is 0. Okay, in dot product, you need to take same unit vectors. In cross product, you need to take different. Clear? This thing is clear, na? Good. Now we're going to do this quickly. Now energy consideration, the same thing we already done. Let's read it quickly. Energy consideration, a quantitative study. We will be concentrating on Lenz law, and Lenz law basically tells about the energy conservation. As we apply the idea of energy consideration in motion or motional EMF, Lenz law and the law of. So bear that in mind. Consider a conductor that is rectangular in this shape. Three of sides of this rectangular conductor are fixed, but one of them side AB is free. Means this is a conductor and one side is going to be free to move. Okay. The resistance of the remaining three sides A, B, C, D, I mean these three remaining sides are going to be very low, and we alter the flux in a magnetic flux. I mean, if we alter the flux in a magnetic field, if we try to change the magnetic flux, so there is a EMF is going to be generated, obviously due to the change in flux with respect to time, d phi by dt. Due to this flux changing, due to this EMF, we have a current I, BLV by R. We know this thing. So there is a energy is going to be, we know this thing. There's a power is going to be force into velocity. We know this thing. So then what we don't know as a qualitative, the work that is being done on this instance is mechanical, and the mechanical energy is lost as a joule heat. What is doing what is the happening here? We are doing a mechanical work in pulling this rod of length L, isn't it? And there is a pulling this particular rod, there is a generation of induced current. When there is a generation of induced current, so always electric current gives us two effects. The first initial effect is heating effect, I square RT. You remember na? Heating energy, I square RT. So if instead of energy I need to find the power, or you can say heating power or dissipated power, that is I square R. Simple. So that is so basically your mechanical energy in pulling this particular rod of length of a conductor L generates a induced EMF, and due to this induced EMF, there is a what is going to be happening there. Due to this induced EMF thing, there is a current, and due to this current there is a heating effect is going to be, and that is the power is going to be lost in the form of heat. That is Pj I square R B square L square V square divided by R. Rest everything is same. The qualitative aspect, the idea to see this thing is changed. Nothing more than that. Moving ahead, energy consideration, a qualitative study. EMF del phi by del T. We have E equals to IR. We know na power P equals to VI. So V this or using Ohm's law, V equals to IR. So from here, as a result, Q charge again this I into del T. If you're putting this everything, you can get this del phi into R. We already do this thing in us so many times. Read this question and try to do that. Just 5 to 6 minutes to attempt a CA if you find something, because after that much long or everything given lecture, I don't feel you get anything. You need anything. Okay, two questions like this, simple one. And then there is a summary, and then we're going to discuss. I give you a hint or something if you want to. In a uniform horizontal magnetic field with a magnitude, this is your magnetic field is given. A circular loop of radius R is given. Circumference is given. Okay. And a circumference of 40 revolution with the angular speed is this. About its vertical diameter. If a closed loop of resistance 30 occurs in the coil, calculate the average power dissipation caused by the joule heating effect as well as the value current in the. So obviously here you need to find induced current first, and then due to this induced current there is a power dissipation, which is How are we going to do that? R is given, B is given. R is resistance beta. Small r is radius, which is 45 radian per second. What is this? 45 rad. Okay, for R. So we know that I equals to E by R, E equals to N omega. Okay. C, omega equals to V by R. So from that particular thing, we don't know V, but we can convert this V. This relation is, yeah, this is my relation. Or this is, tell me with anyone. Angular velocity is equals to linear velocity into the this or this. I'm confusing this always. Okay, so do this conversation. Conversation. No, conversation is not correct word. No? What is the correct word? Transformation. Okay. In the formulas, there's a I equals to E by R, and induced EMF for a circular thing is N omega AB. A is area, B is magnetic field, N is number, as well as we have E equals to BLV. Okay, N BLV, if I'm saying so. So L here is perimeter. Okay, which is 2 pi R L, and R into V, that is gives me omega. So that is the thing. Wait, this is going to be then. Okay, and instead of A, I can write A is here, not area, but A is here, perimeter. Is this clear, everyone? 2 pi R L equals to this, and then N equals to pi R square into omega B, and then this and this. Okay, once just check this relation. I'm not clear with this. Okay, check and tell you in the next. So use this particular formula. Simple. N omega AB. A is area, omega is angular velocity, which is V into R, and then B is magnetic field, N is number. Simple. Putting everything, because in this terminology we have everything, and then you can get the EMF and you can get the I, E by R simply, and then you can get the power loss and so and so. Okay. In a same sense, this particular question is related. A wire with a resistance of 20 ohms and a length of 2 meter is applied in a uniform magnetic field of strength 1 Tesla. The wire is rotated through an angle of 90 degree in 0.5 seconds. Calculate the heat energy generated by the wire during this time. The same thing is going to be happen here. Calculate the heat energy, right? Calculate the heat energy means heat energy you need to find. And the same thing, like change in flux through the wire is del phi B A cos theta. So first of all find this, then heat energy by the wire del Q del phi B into R, because there is no change in flux, so the heat energy is 0. C. Okay, here the correct option is C, because that is 30 degree, 90 degree. B A cos 90 degree. So when this is 0, everything is 0. Nothing matters then after this. Is this clear, everyone? The last question we were doing. Now you can attempt the CA as well as. Okay. So this is the done by my side. So in this particular class, we cover most important things like Lenz law and conservation of energy, motional EMF, translational and rotational EMF, and transformer EMF, energy consideration, a qualitative study.